One of the major challenges in simulating multi-phase flows is the advection of the marker function that identifies the different fluids. There are two main ways to do so. We can update the marker function directly by solving an advection equation, or we can move the interface separating the different fluids and then reconstruct the marker function from the location of the interface. Here we do the latter by placing connected marker points at the interface and then moving them with the flow. When we use connected marker points to advect an interface for complex three-dimensional flows, it is important to use a data structure for the interface that allows for maximum flexibility in updating the location of the points and their connectivity, yet is sufficiently simple so that it can be easily understood. Indeed, for such flows, the data structure can determine how easily the code is developed and new capabilities are added. For two-dimensional flows, on the other hand, essentially any data structure can be made to work relatively easily. Here, we will use a particularly simple data structure and represent the interface by ordered marker points. While this results in a loss of flexibility, it works well for simple problems and provides a straightforward introduction to the use of connected marker points to advect interfaces. We'll start by implementing the approach for flows where the only difference between the different fluids is the density and where surface tension is zero. We'll also use a first-order time integration as we used for the flow solver. Surface tension and different viscosities, as well as higher-order time integration, will be added later. We will start by assuming that we are only dealing with one interface and that it is closed, thus representing a bubble or a drop embedded in a different fluid. Since the points are ordered, we use an index L that takes on the values 1, 2, 3, and so on, until we have enough points to discretize the entire interface. We'll take this number to be NF. To simplify dealing with the first and the last point, we introduce two ghost points on either end, so the total number of points is NF plus 2, and the interface is resolved by points 2 to NF plus 1. The coordinate of point number 1 is set equal to the coordinate of the last point resolving the interface, point NF plus 1, and the coordinate of point number NF plus 2 is set equal to point 2, the first point used to resolve the interface. By using the ghost points, we can treat all the points on the interface in the same way, and then simply update the ghost points in a separate step. If the initial shape of the interface is a circle, its construction is particularly easy. Once we have decided where the center of the circle, xc and yc, is, where we start and in what direction to go, the coordinates are easily found. We can obviously start anywhere and go either clockwise or counterclockwise, but here we start directly above the center and go in the counterclockwise direction. The x-coordinate is given as the x-coordinate of the center minus the radius times the sine of the angle from the vertical axis, and the y-coordinate is then given by the y-coordinate of the center plus the radius times the cosine of the angle from the vertical axis. The angle increment is 2 pi divided by the number of points used to resolve the interface, nf minus 1, and we increment it by L minus 1, where L is the point number, since we want to start with a zero angle, so the first point is directly above the center. Since we are using two grids, the fixed regular structure two-dimensional grid, where we solve the fluid equations, and the one-dimensional moving grid, which we use to mark the interface and construct the density and the surface tension, we need to transfer information between those two grids. The easiest way is to start with a point on the interface and ask what point on the fixed grid is closest. This, as we will emphasize again later, is a much simpler problem than asking what interface point is closest to a given grid point. Thus, we try to always start with an interface point and find the closest point on the fixed grid. How this is done is perhaps best explained by assuming a regular structured one-dimensional fixed grid with evenly spaced grid points. Here, the grid points, or the location where we store each value, are denoted by small circles, and short vertical lines indicate the boundaries of the control volumes. For simplicity, we start by identifying the first point, located on the left boundary, as grid point number 0. For a one-dimensional problem, the front is a point, and we can find the fixed grid point to the left of it by dividing the location of the front by the distance between each grid points and taking the integer value. The standard way of converting a floating point value to an integer value takes the value to the left for positive values and the value to the right for negative values. We want the value to the left for all cases and therefore use the floor command instead of the int command. In our implementation, where we use a staggered grid, the first point is on the boundary in some cases, such as for the horizontal velocity, but for the vertical velocity, the pressure and the density, it is half a grid spacing outside the domain. Furthermore, the index starts from 1, not 0. The expression on the last slide is, however, easily modified. When the first grid point, with I equal to 1, is on the boundary, we simply add 1 to the index found earlier, and when the first grid point, where I is equal to half, is half a grid spacing to the left of the boundary, we add half delta x to the location of the front before applying the floor function. Since the index for the first point is 1, we also need to add 1 as for the first case. In many cases, the information that an interface point needs must be interpolated from the fixed grid. This is the case for the velocities as well as quantities like the temperature in problems where we include the energy equation. Once we know the location of a front point with respect to the fixed fluid grid, the interpolation is straightforward. Assume that a point on the front denoted by the subscript f is located between grid points I and I plus 1 in the x direction and between j and j plus 1 in the y direction. Since the value of the quantity that we want to interpolate, call it phi, at the front point must be the same as the value at a grid point if the front point location is the same as that of the grid point, we can write down a linear interpolation function directly. This expression relates the value of phi on the front to the value at the grid points around it, and it should be clear that the expression for phi on the slide is linear in x and y, it is bounded by the grid values, and that phi at the front is equal to the value at a grid point if the front is moved to that grid point. Notice that since the different velocity components are stored at different locations or on different grids, we need to interpolate those separately. We can rewrite the interpolation function in a slightly more general form by identifying the quantities multiplying the grid point values as weight. For a linear interpolation, the weights have a simple geometric interpretation. The weight for grid point I, j, for example, is given by the x-coordinate of the I plus 1 grid line minus the x-coordinate of the front point times the y-coordinate of the j plus 1 grid line minus the y-coordinate of the front point divided by the area of the grid cell, delta x times delta y. This is the area fraction of the rectangle above and to the right of the front. Similarly, the weight of the I plus 1, j plus 1 grid point is the area fraction below and to the left of the front point. The weight of the I, j plus 1 grid point is the area fraction below and to the right of the front point, and the weight of the I plus 1, j grid point is the area fraction above and to the left of the front point. Thus, for each grid point, the corresponding weight is the area fraction of the area in the opposite corner. Obviously, the weights must sum to 1, and for the area fraction this is easily shown to be the case. In the code, we loop over the front points, and for every one of them we determine the closest point on the fixed grid. Since the different velocity components are on a different grid, we must interpolate each component separately. The area weighting is just one possible interpolation function. Sometimes it is desirable to use higher order ones that involve larger number of points on the fixed grid. The weights are then different, but they still need to sum to unity, and generally we require the weights to ensure that the front value is not just bounded by the grid values, but that if a front point coincides with a grid point, then it gets the value at that grid point. Smoother weights can sometimes be important. Surface tension is high or the density ratio across the interface is large, but I should emphasize that the simple area weighting presented here works very well for a wide range of problems. Once we have interpolated the velocity of the front points from the fixed grid, we are ready to move them. Here, we move the front points in the simplest way possible and use an explicit first order or Euler method where the new location of a front point is its old location plus its velocity times the time step delta t. Notice that we generally move the points with the full velocity interpolated from the grids. Strictly speaking, we only need the normal velocity since the tangent component only slides the point along the interface without changing its location or shape. The code to move the interface points consists of two parts. First, we interpolate the velocities from the fixed grid, and since the different components are located on different grids, the simplest approach is to interpolate them separately. For each interpolation, we first identify the grid point to the left and below the front point, then we find the area fraction corresponding to the location of the front point relative to the grid point, and then we interpolate from the four closest grid points. Once the interpolation is done, we can move the points to their new locations using a simple explicit first-order method. Later, we will increase the accuracy of the advection to second order, and obviously we could implement an even higher order scheme if we elected to do so. As the front points move, their spacing will generally become uneven. Some points will move apart and some will come together. Since it's only the normal velocity of the points that matters in determining the new location of the interface, we can slide the points along the interface to attempt to keep the interface resolution relatively uniform. Sometimes, however, we need to add points if the interface stretches, and sometimes it makes sense to take out a point if they become too crowded. Maintaining the distance between the grid points as uniform as possible can be done in many different ways, and for two-dimensional flows, almost any strategy that we choose can be made to work relatively easily. In our case, where the points are ordered, the updating becomes particularly simple. Here we present an approach based on keeping the spacing relatively uniform by adding and deleting points as needed, but leaving other points where they are. Leaving most of the points untouched should minimize interpolation errors. Since we want to have about 2 to 4 points per fixed grid cell, we add points if the distance between the 2 points is greater than half the cell size, and we delete points if the distance to the next point is smaller than a quarter of the cell size. We start by copying the point location into a temporary array. We then put the first point back to where it was, and then compute the distance between the second and the first point, assuming that it is a straight line. Using the figure on the right-hand side of the slide as an example, we see that the distance falls between the minimum and the maximum, so we simply copy point number 2 back to where it was. Point number 3, on the other hand, is too far away from point 2 that we copied back into the original array, so instead of copying it into the original array as point number 3, we insert a new point into the number 3 slot, taking the location of the new point as the average of new point number 2 and old point number 3. Then we compute the distance of the old point number 3 from the new point number 3 point, and finding it to be acceptable, that is between the minimum and the maximum, we copy old point number 3 into the new array as point number 4. The distance of old point number 4 from new point number 4 is acceptable, so it becomes new point number 5. However, old point number 5 is too close to new point number 5, so it should be deleted. This is accomplished by simply not copying it over into the new list and moving to old point number 6. Its distance from the new point number 5 is fine, so it is copied into the next open slot in the new array, which is number 6. We continue to copy the points over one by one, adding points when the next old point is too far away from the last new point, and skipping old points if they are too close to the new points, until we have examined all the old points. The code to accomplish this is relatively straightforward and consists of only a few lines. In the first line, we copy the vectors holding the x and y coordinates of the front into temporary files called xold and yold. We then loop over the old points, checking the distance between the last new and the next old point. If the distance is too large, we add a point. If it is too small, we don't copy the point and move on. If neither of those hold, that is, the distance is neither too large or too small, we copy the old point over. In the last line, we set the ghost point. I should emphasize that the simplicity of this algorithm is somewhat deceiving, since it is really uniquely designed for ordered point in 2 dimensions. For unstructured grids, as we generally need for the fully 3-dimensional case, maintaining the resolution is generally a more complex task.